begin with, just sort of a quick recap of how gravitational wave astrophysics works. So this is a field that is based on using gravitational waves to observe the universe. So here I've got a picture of the first gravitational wave signal, GW 150914, and a sort of artist's rendition of the kind of source system that produced it. So the signal can kind of be divided up into three parts. The in spiral, where you have, in this case, a binary black hole, and the two components are orbiting around each other and producing gravitational waves with increasing frequency and amplitude. The merger, where they sort of rapidly plunge together and collide, producing that kind of spike, the strongest part of the signal, and then the ring down as the signal sort of starts to decay after the merger. And the point is that in gravitational wave astrophysics, you're trying to use this gravitational wave signal in order to make inferences about the source system that produced it. So as I talked a little bit about last week, the LIGO-Virgo collaboration uses a network of detectors. This one is Virgo in Italy, but there's also LIGO Livingston and LIGO Hanford in the US. And these collect information about the gravitational waves that are passing and hence about their source events. And I mean, I talked a bit more about the details last time, but for the purposes of today, I'm just going to, well, the overall methodology of LIGO can sort of be summarized in this schematic. Obviously, this is still very simplified, but of this sort of simplified sense of the schematic, of the methodology, I'm just going to be talking about two features: the template matching, which is the way that you search for gravitational waves, and the parameter estimation, which is basically how you make inferences about the source system, or in a sense, observe binary black hole mergers or other compact binary mergers. So since last week, I already talked about the match filtering procedure. I'm just going to emphasize a few things that I think are sort of epistemologically relevant for what I'm going to say today. First of all, the most efficient way of searching for gravitational waves in the data involves searching using templates, and they in fact are searching for this. They've got a whole library of 250,000 such templates that are being searched for in the data. The second thing is that in order for there to be a sort of what's considered a genuine detection, there need to be coincident triggers in at least two of the detectors. That is, at least two of the operating interferometers need to sort of have this search procedure indicate that there is in fact a gravitational wave signal in the data. And the idea here is that you've got a kind of common cause explanation. The idea is that in order to think that there really is a gravitational wave signal passing, you need a signal present in both detectors. If there's a signal present in both detectors, you sort of infer that there must be some kind of common cause producing that same signal. It's not just sort of random chance due to noise. And the way that you sort of, the way that this is established, and here I have a very sophisticated diagram to illustrate this. In order to sort of guarantee, well, in order to suggest that this is not merely noise producing triggers in both of the detectors, a background of data is generated using time slides. So what this involves is essentially shifting the timestamps on the data in one detector relative to the measured strain, so that any genuine signals between in the two sets of data will no longer be correlated. And so any correlations that pop up when you do the search must be produced by noise. So by sort of repeating this procedure, you can generate a background and estimate how often noise is likely to produce false signals. Now, parameter estimation is, here we're talking about the source system. So if theta is some kind of collection of parameters in the data, then you can use a Bayesian analysis in order to basically generate posterior distributions for a whole set of different parameters. Doing so requires having some model that takes a source system and maps it to the gravitational waves that would be produced, as well as some prior information, here represented by I, and of course the data. Now there are about sort of 15 physical parameters about the source system that are being estimated here. Some of these are intrinsic parameters, that is, things to do with the binary system itself, like the masses of the components and the spins. Others are extrinsic parameters, so things about the relation between us and the source system. Things like the distance, the position in the sky. In addition to this, the parameter estimation also needs to take account of calibration uncertainties and basically use the same process in order to give posterior distributions for these. And this introduces of the order of about 10 extra parameters per detector. So a typical 3-detector analysis is going to end up sampling 45 parameters. And the LIGO Virgo collaboration has developed something called LAL inference, which is a stochastic sampling library. And it uses 2 different algorithms in order to perform the parameter estimation. One is a parallel tempering Markov chain Monte Carlo algorithm, and the other is a nested sampling algorithm. But sort of the take-home message of this is that LAL inference performs a Bayesian analysis in order to get posterior samples for all of the 45 parameters. So I've just told you that gravitational wave detection, as well as binary black hole merger observation, involves using models or templates. So I need to tell you a little bit what those models are, what modeling approaches are used. So here I've listed the 4 of the main modeling approaches that are relevant here. So I'll just go through them relatively quickly and also mention their sort of domain of applicability. So first of all, post-Newtonian models are based on general relativistic corrections to the Newtonian solution, expanding the Einstein field equations and powers of v squared over c squared, where v is the characteristic orbital velocity of the compact binary. These are sort of well-established, this is a well-established approximation scheme, and it's thought to be really good at modeling the early in-spiral, where the separation between the compact objects remains quite large and the orbital velocities remain quite small. But it's less good once you get sort of to the late stages of the merger. Black hole perturbation theory is another useful tool for modeling compact binaries, but especially with extreme mass ratios, because in this case you can model the smaller object, the motion of the smaller object by basically introducing perturbations in the background metric of the larger object. With LIGO Virgo observations so far, I think with this been maybe 1 or 2 confirmed observations so far where they even think that one object is clearly larger than the other. So we're not really dealing with extreme mass ratios in that case. So I'm not really going to focus on that one in particular. Now, one of particular importance is numerical relativity. So this is models, what I'm talking about here is models generated using highly sophisticated simulations on supercomputers that can take of the order of months. And these are supposed to be solving the exact Einstein equations numerically. And these are thought to be extremely accurate even for the plunge and merger, that is the very late stage of the merger, but they are of course extremely computationally expensive. So generating a 250,000 waveform template library from numerical relativity simulations alone is just not going to be on the cards. Now, in principle, the domain of applicability for the numerical relativity simulations could span the parameter space, but they become extremely computationally expensive if you have to start them for the early in spiral. And it's going to be a very long process. Or for extreme large mass ratios, similarly very costly, which is why they're sort of limited to that smaller area of the graph. And finally, we have the effective one-body formalism. So this is a formalism for producing quasi-analytic models of the binary mergers. And the ideas behind this approach is to transform the conservative dynamics of two compact objects into the dynamics of some effective particle traveling in a deformed Kerr metric. So in the end, it's actually the effective one-body models, or some kind of version of them, that is used for the templates, because they can sort of they're a tunable model that can be used to actually span the whole parameter space. Oops. Now again, we have another highly sophisticated diagram to illustrate some of the relationships between these different modeling approaches. So yeah, these modeling approaches are sort of very intertwined. So first of all, the effective one-body and numerical relativity models have to take post-Newtonian results as input. Numerical relativity simulations need initial data, and this comes from either post-Newtonian or effective one-body models. The effective one-body models are tuned to numerical relativity simulations in order to sort of make them in order to sort of make them accurate descriptions. They have to be tuned to numerical relativity results. And then you sort of extrapolate throughout the parameter space and end up testing the effective one-body models against other numerical relativity simulations, just as sort of a test that things are going well. And at least one of the main sets of templates that are used by the LIGO-Virgo collaboration are EOBNR models, which are basically effective one-body models that have been tuned to numerical relativity simulations. Now, just to tie this in briefly with what we were talking about last week, so the LIGO-Virgo collaboration describes the observation of GW 150914 as the first direct observation of a binary black hole merger. Since this is like the first observation of such an event at all, there's not sort of the clear distinction being made as there was when they claimed that it's the first direct detection of gravitational waves. In that case, of course, the contrast was with the Hulse-Taylor binary detections. Here, there's less of a clear contrast. So I don't think we can say for sure exactly what's meant here, or really even evaluate the claim exactly. But I think it's worth pointing out some senses in which this observation of a binary black hole merger counts as direct or indirect. So first of all, it's clearly direct in the sense that the gravitational waves are traveling from the source to the detector with very minimal interference. So in the sense of Shapiro, which I mentioned last week, this is what's meant by direct observation. And so on this account, the observation of binary black hole mergers by LIGO would count as direct. But there's also some senses in which it's pretty indirect. So first of all, of course, there's significant interference with the signal within the detector. The output data is extremely noisy. And also when you consider the sort of calibration modeling and the calibration uncertainties, the sense in which the data reflects the parameters of the source system is a little bit more messy. And secondly, and of sort of more interest for today, these inferences are based on, the inferences about the binary black hole system, the source, are mediated by a sort of web of interrelated models and simulations. And so the inferences that you make based on the gravitational wave signal about the source are just a little bit more messy and convoluted, I suppose, in terms of how exactly you validate the observations. Okay. And yeah, note that I mentioned that there's a sort of epistemic advantage conferred on a direct gravitational wave detection over an indirect one, mainly in that it relied on it mainly relied on the modeling of the detector system for its sort of validation, rather than having to worry about a model of a separate target system. Clearly, that's not going to carry over to the observation of binary black hole mergers, because these observations are very dependent on models of the source system. Okay, so I think it's very natural to worry based on the fact that I've said that both the detection of gravitational waves and the observation of binary black hole mergers is highly model dependent. There's a sort of an obvious concern that there might be a theory-ladenness or model dependence of the observation, and that this might be in some way problematic. So first of all, when it comes to the detection of gravitational waves, we can ask whether we should be worried about the reliance on models to observe these signals using that template matching process or matched filtering. Now, I want to sort of resist the automatic jump to thinking that this is going to be a problem, in part because I think this is a very general problem, or at least it's a very general feature of the experimental process. Measurement sort of generically involves model-based inference. And insofar as this is a problem, it's at least a very general problem. And while match filtering might be a very sort of clear case of it, I think it's at least not a particular problem for LIGO. That said, I think there are some sort of three particular worries that we might have about how the reliance on models might be a problem for the methodology here. So the first one is one of false negatives. Basically, if we can only detect things when we have a corresponding template, then we might be missing really interesting signals. I think it's worth noting that the signals would have to be quite different from any existing templates in order to not be picked up. And also that LIGO does in fact have an unmodeled search pipeline. So, you know, it's hard to assess what might be being missed. And of course, if anything is being missed, then this would potentially be very interesting things being missed. But I'm at least not sure how worried we should be, given that there are in fact these sort of more agnostic unmodeled searches.
So
the other, sorry?
Do you have time for questions now?
Yeah, you can jump in if you have a clarificatory question.
So when they were announcing that there was indeed a detection, there was this 5 sigma threshold for detection, and given the dependence on the particular models, these statistical uncertainties must be tied to particular models. So can you imagine how the uncertainties in the quote unquote detection threshold would be if some other assumptions went into the how good the modeling templates were? So if you're, I guess I just think that there is probably much larger systematic uncertainties than the than the statistical ones, and it kind of ties into what it means to be a known unknown versus an unknown unknown. I mean, I think that there were neutrinos that were found to be moving faster than light with some exquisite statistical uncertainty, but of course there was a really bad systematic, which was the wiring of the detection systems was off, and there was really no supplementary statement of how big they expected the systematics to be. So is there any sort of range of like how much do the statistical uncertainties depend on some possible systematics that you can think of in a setup like this, where you need assumptions to make templates and assume that they're somehow valid with the system that you're looking at?
So I'm not sure I'm quite thinking about this in the same sort of framing as your question here. So, I mean, I actually think you don't need to be that worried about the fact that they've made a detection. I think that any concern going to be much more to do with the fine-grained details of whether you've got exactly the right signal and the inferences you make on the basis of it. But I think maybe I'll just continue because I'm going to sort of address those kinds of issues, and maybe we can return to the question at the end, and you can tell me whether I've answered it or whether maybe, right, so I was saying that there's, of course, there's this concern about false negatives. I think that at least the bigger concern for LIGO, at least initially, was the possibility of false positives. So I think this is maybe slightly more what you were getting at, Richard. So the possibility of falsely identifying noise as a signal. So this, of course, would be a really big problem if it was happening, if you were detecting noise and thinking that it was a gravitational wave signal. But this problem is one I think that the LIGO methodology is particularly well suited to dealing with. For one, because you have that requirement of having simultaneous signals detected in multiple detectors with the same template. And like those and because the noise is thought to not, I think it's not thought that there are plausible sources of noise that could be correlated between the detector. So something like a lightning bolt is not likely to sort of produce correlated signals between the two detectors. And the other thing is that the way that these sort of uncertainties are calculated, the statistical significance is calculated, is using that time slide process that I talked about at the beginning, where you are precisely trying to estimate the sort of background rate at which noise in the detectors could sort of randomly generate sort of candidate detections. And in the case of GW 150914, I think they estimated that the likelihood that it was produced by noise was something like 1 in 203,000 years. So in terms of at least like detecting a gravitational wave signal and thinking that it really is a signal, I don't think we should be so worried about the LIGO methodology. The concern that I'm sort of most worried about is somewhere in the middle, and that's my bullet point 3, which is actually imperfect signal extraction. So this is the case where you successfully detect a gravitational wave, but the signal that you extract doesn't completely represent the gravitational wave. So essentially there's some kind of mismatch between the template and the actual signal that it's extracting. This, of course, could lead to really big problems once you start to make inferences about the source system, because you're sort of systematically biasing the inferences you're making. So if you detected a lower amplitude, you might overestimate the distance to the source, or something about its inclination. And if you're consistently doing this, then you're sort of biasing the whole population of observations. So, right, all of these problems are arising in part because of the sort of question about whether or not the models being used are good descriptions of the systems in question and the resulting gravitational waves. And there's sort of two potential worries here. Firstly, that the models are inaccurate relative to general relativity. So they sort of aren't actually accurate solutions corresponding to the systems they are sort of purporting to represent. And the other possibility is that basically GR is inaccurate when it comes to describing the dynamical strong field regime, so the very late stage of the merger. And to use some terminology from Unison Pretorius 2009, think of the first one as a kind of modeling bias, and the second one as, in their terms, fundamental theoretical bias. So I'll start with the first one. How do we know that, say, the EOBNR templates or models are accurate relative to general relativity? So for a start, there's no analytic solutions for these kinds of systems to compare to. And much of their validity or their justification is derived from numerical relativity simulations, which are sort of acting as benchmarks for these models. But then, of course, we have to ask why we think that numerical relativity simulations are accurate. Now, to some extent, if you're not a numerical relativist, you just have to trust that what they're doing makes sense. But some of the more sort of accessible reasons for thinking that numerical relativity simulations are accurate come from things like convergence studies or code comparisons. And since there are some very different methods for doing numerical relativity simulations, successful code comparisons are, I think, somewhat impressive in this context. Now, when it comes to theoretical bias, this is sort of the possibility of general relativity not being an accurate description of the late stages of these events. So why is it we think that general relativity is accurate, provides an accurate description of a binary black hole merger? Now, you might think that we just have sort of good general confidence in general relativity based on previous tests. So, for example, the Hulse-Taylor binaries provide some good evidence that general relativity is a good description of those kinds of systems. However, those tests weren't probing the same physical regimes, namely the dynamical strong field regime, where velocities are large and the gravitational field is very strong. So then you might hope that the LIGO observations will come to the rescue, or it should be LIGO and Virgo there. Because these observations of the dynamical strong field regime will come to the rescue and show that the models we've been using are indeed accurate descriptions of the system in question. But the trouble is that these observations are very reliant on those very models. And so insofar as those models are presupposing that general relativity does provide an accurate description of those systems, it looks like they're not going to be very good for testing whether or not general relativity is in fact accurate for those systems. So we end up with the circularity problem, where justifying the observations or ensuring that our observations or the parameters we infer about the system are accurate relies on having valid models, but validating those models is in turn reliant on those very observations. And by way of quick diagnosis, I mean, I think some kind of circularity problems concerning model validation and observations are maybe somewhat of a general feature of science. I mean, Harry Collins talks about these in the context of detecting gravitational waves, of course. But this circularity is a slight, I think, exacerbated by various features of the epistemic situation. So Of course, in this case, the systems we're interested in are very distant, and we can't manipulate or intervene on them. And essentially, this is astrophysics. And so we also don't have any independent empirical access to those target systems to sort of check that what we've been doing makes sense, sort of break that circularity. And of course, these mergers are occurring in previously unobserved physical regimes, which gives us sort of extra reason to be concerned that our models might be inaccurate, or at least that we don't have reason to be confident that they are accurate. Okay, so in the last few minutes, I'm just going to briefly go through how, nonetheless, despite this, from what I've just said, it might seem that LIGO and Virgo are in an impossible situation, and there's just no way that they could possibly bear on whether general relativity is correct. However, they do in fact claim to be doing a whole bunch of different tests of general relativity. So I'm going to go through, at least briefly, a list of some of those tests. First of all, of course, the very detection of gravitational waves can be seen as a test of general relativity, at least insofar as Newtonian physics doesn't. We don't expect there to be gravitational waves there. So in some sense, this is some kind of confirmation of the predictions of general relativity. Of course, not exactly a very fine-grained one, and not one that's going to sort of rule out the sort of viable candidates as alternatives that we might have in mind. 2, 3, 4, and 5 are all tests that were performed based on the original observation of GW 150914. So I'll go through each of those in turn. And then finally, I'll just talk briefly about what multi-messenger events might add. Okay, so one of the problems that I mentioned before was the possibility of imperfect signal extraction. So it turns out that one of the tests that LIGO Virgo conducts is basically trying to rule out there being any signal remaining in the data after the signal's been extracted. So what they do is they take the best fit waveform and subtract that from the data, that is kind of removing the signal. And the residual, so that's that, it's that bottom part there, underneath the third one down. That residual after the subtraction is then compared to sort of normal detector noise where there's not thought to be any signal present. And so what they then say is that we use this estimated level to bound general relativity violations, which are not degenerate with changes in the parameters of the binary. So this is of course significant because so what they're doing here is ensuring that they've completely extracted a signal, and that means that they have properly extracted all of the signal. However, it's still possible that there's a degeneracy between the signal that's been extracted and is sort of connected with some source system with a set of parameters describing that system. It could be actually that's the same signal that you would get from a very different system if some other theory were true. So there's a sort of remaining problem, even if you're extracting the signal perfectly. That alone would sort of not ensure that just because you've extracted a signal adequately with a GR template doesn't necessarily mean that GR is providing the right description of the source system. So in a sense, this isn't necessarily a strong test of GR, but it's certainly a very important test of signal extraction. The second test, the low-high frequency test, as I'm calling it here, this basically, so you have the low frequency part of the signal, or I suppose I should go over here to because I'm mirrored. You perform parameter estimation based on that early part of the signal. And remember that that's the part where, say, post-Newtonian models are thought to be very accurate. And we shouldn't really expect there to be deviations from GR in that regime. Then you perform parameter estimations for the high frequency part, where there may indeed be deviations from GR. And then sort of connect those two estimates using formulas for numerical relativity. And then that's sort of a consistency check, because if it's the parameters that you infer based on the early part of the signal don't mesh with the parameters that you estimate based on the late part of the signal, even though you've kind of assumed general relativity and used numerical relativity for that entire process, nonetheless, you could come up with some inconsistencies, which would hint that in that high frequency part of the signal, something interesting was happening. So the phenomenological deviations test basically involves altering the templates. So, for example, take GW150914 and the template that actually extracted the signal for that, and compare that with a generalized set of analytic waveforms that include parameterized deformations with respect to GR. So basically these deviations from GR being modeled as some kind of fractional change in any of the parameters for the gravitational phase expression in the base waveform model. Yes, the idea here is basically that you're just generating a whole set of templates in which you're sort of turning some knobs and changing some parameters, you're deforming things such that those templates are no longer GR models. You're sort of expanding the space possibilities. Then you sort of re-perform your parameter estimation with that sort of more generalized set of models, and basically just check whether the GR values are within the posterior distribution. And for more on this particular test, I highly recommend the work of Lydia Padden, published in 2020. And finally, a very similar thing can be done by modifying the dispersion relation. When I'm running out of time, so I'm just going to just zoom past and get to the end. Again, more tests are available once you have an event like GW170817. The fact that you have an electromagnetic counterpart provides some kind of check on the fact that everything's working well. And of course, you have the arrival times from the electromagnetic signal, and the gravitational wave signal provides a further test of GR. Now, yeah, I'll just go into my conclusions. So what I've said so far is that the detection of gravitational waves and the observation of binary black hole mergers, both of these are highly model-dependent processes, and they're both dependent on having accurate models or templates of both the source system and the gravitational waves that are produced. These models are sort of mediating between the theory, general relativity, and the world or the observations. And LIGO and Virgo face a sort of circularity problem due to this model dependence, and especially with respect to the observation of binary black hole mergers. I think that what's interesting about the tests of GR that I just sort of briefly went through is that each of them are sort of looking for evidence that that template-based approach could be biasing the results. So the residuals test is looking for ways that reliance on templates could be messing with your signal extraction. The low-high frequency test is looking for ways that the parameter estimation based on GR could be sort of leading you astray. Each of these tests is sort of looking at different aspects of the methodology and ways that the model the model-dependent observations could be biasing the results. And so I think that all of these tests can sort of be understood as a response to methodological concerns about circularity and, again, what Eunice and Pretorius call modeling or fundamental theoretical bias. Okay, thank you. Looking forward to questions.
Well, thank you very much, Jamie. We had a few things that took up some time. So if you want to, in the Q&A, if you want to develop on anything that you feel like you would have liked a bit more time on, then please do so.
Okay.
There is a raised hand from Peter. And
thank you. A really
Eric
good
and
talk, as was the one before. I think it very systematically approached. There are many different issues that merit discussion, sorting out the direct, indirect, the relationship between establishing GR, establishing gravity waves, establishing black holes. And I wanted to focus on whether there have been events that are neither environmental nor fitting a template. In other words, are the templates so spanning of the space of possible results that there's always a good enough template to account for every event that has happened? Or have there been some events that don't qualify, that aren't excluded by seismic or coincident garbage trucks in 3 locations or whatever it is, and but also don't fit a template? Is there? Yeah.
So far, all of the confirmed detections, that is the sort of publicly announced detections, have been detected by the template-based searches, I believe. That said, so with O3, they have been announcing candidate events as well. And I think that there was at least one so-called burst search detection. Now, whether or not that actually pans out and being sort of validated as a genuine detection, I'm not sure. And of course, so it is in a way more challenging to validate any detections using the unmodeled searches. It's a problem that they've, I think, grappled with for quite some time, because I mean, those unmodeled searches are really good at finding big noise spikes. In fact, one of the big uses of the unmodeled searches is to rule out data that has, too much noise in it. And so if you're not using the models in the process of the search, you have to take account of the modeling at some point later in the process in order to sort of actually claim that this is a real detection rather than just coincident noise.
Tom, you had a...
Yeah. Thanks, Jamie. I really enjoyed the talk. Thank you so much, and going through the early little battles as well. So I had a question which is related to Peter's and probably bounces off the third of your bullet points on this this last concluding slide. Really important work to evaluate just how theory dependent and arbitrary, but to some extent the circularity problem is true of everything we do, all of science. There isn't an experiment that isn't theory laden, that isn't theory induced. So it can't be that there's a qualitative special circularity going on here. It must be quantitative. So I wondered if behind your thesis here is a sort of quantitative assessment of circularity, or quantitative assessment of just how circular different investigations are. But I wonder if that's true, and if it has anything to do with the parameter counting you were doing before. So you had, I think, we're 45. I think and maybe in the detection of the Higgs particle, that's only, you know, a 22 parameter circularity or something. So quantitate. Can you quantitate that? Quantize that. Quantify. Sorry. That state. Is that what's going on here? Is there a way of measuring circularity in the way we do science?
So I suppose I never would have thought of it as being a quantitative thing. I guess I was conceptualizing it more in terms of, I guess in a way, layers of things that are making things difficult. I mean, so with any experiment, if you're trying to sort of, in a sort of normal, ordinary experiment, the way that you go about trying to break the circularity is things like, you know, calibrating your detector. Testing it with sort of known signals, controlling the input and seeing what the output is. You do enough of these things, that seems like a way, at least if you're not Harry Collins and more of some of his more extreme moods, then you think that that's the kind of thing that can in fact break the circularity. What I think is going on in in astrophysics, you're actually sort of adding this extra problem, which is that you can't do most of those things.
Right. So unlike radio astronomy, we can make radio waves, or optical astronomy, we can make light and test our telescopes. We can't make gravitational waves, so we can't test or calibrate our gravitational telescopes in that way. Is that what you're saying?
I think that's actually two separate things. So first of all, in all of astrophysics, you have the problem where you don't have access to the target system. You can't sort of go to a black hole or to a star or to any kind of astrophysical system and manipulate it and, you know, do the kind of things that you would do with an ordinary experiment.
Sure.
And so, of course, astrophysicists try to find ways around this, one of which is, say, observing the same kind of system through multiple windows. So the other problem with the LIGO Virgo observations is that you don't have clearly that kind of option, because you just get this one gravitational wave signal from the system and then you're done. So there's sort of these layers of difficulty being added on top of one another. Now, I mean, it would be interesting to think about whether you can sort of try and quantify that. I'm not sure, but yeah.
You have more layers. I can see more layers. Thank you. That's exactly what I was after. That's very, very helpful. Thank you.
Eric has a raised hand.
So Jamie, I think I'm gonna ask a question that actually follows very naturally on what Peter and Tom were just talking about, but coming at it perhaps from a slightly different direction. So I think that when one poses the question, what is about circularity and theory-ladenness, and we tend to talk very blithely about these models depending on GR. But it's not exactly clear to me what is meant by GR. There are, you and I have talked about this before in the past, and I want to press you further on this. So for instance, what do we really mean by GR? Is it the Einstein field equation? Is it how one calculates stress energy tensors? Is it how one computes or constructs generalizations of the Ricci-Leary equation for non-geodetic congruences? Is it how whether one derives or presupposes geodesic principles? There are all of these different equations, formula, relations, principles that we use in what we call the theory of general relativity. And it seems to me it would be more fruitful, instead of asking, does this model depend on GR? Does this network of interrelated models and the analysis that we use them depend on GR? Rather, kind of prizing apart all the different things that actually go into it, and see whether we can isolate which model depends on which bit that we think of as GR. Which model actually depends on the Einstein field equation, the full Einstein field equation. Because in fact, almost all of this is vacuum. So arguably, we never use the full Einstein field equation. All we're using is Ricci equals 0. But Ricci equals 0 is consistent, as a field equation, is consistent with an enormous number of different space-time theories, not just GR. How one derives generalized Drake-Chigurh equations for non-geodetic congruences is arguably completely independent of GR. That's just like kinematics, that any space-time theory in a very, very broad family will can avail itself of. So so I guess I have two questions then after this setup. One, do people in this field try and do that? Do they really try and say this model, it's not just that it depends on GR, but it really depends on this principle. It really depends on this specific, relation or idea, not depends on GR. How much of that actually happens? And second, just out of curiosity, what do you think personally? Do you have an opinion on what is essential to GR that LIGO, Virgo might be or might not be testing, or might or might not be circular with respect to?
Okay, well, as always, wonderful, rich, and detailed question. And I'm getting some, post-traumatic flashbacks to my defense at this point. Okay.
Good,
so,
that was my intent. Excellent.
So where to start? Okay, so I think that one important, so the framing here that I have in mind is that LIGO Virgo would really like to find deviations from GR. They would like to find some kind of evidence that something doesn't quite match up with predictions. And so I think, when I'm talking about deviations from GR, there's going to be a lot of things that are, even if GR is not the right theory for these regimes, a lot of things are not going to be detectable by LIGO Virgo. They're, insofar as theories are predicting very similar things in ways that you sort of suggested. You could very easily end up with the case that the models are just not sensitive to those changes. And so, yeah, there's a sense in which when I say that it depends, these models depend on GR, that's talking with a very broad brush, because as you quite rightly pointed out, there are a lot of ways that these models could equally have been derived from some other theory, I guess, or within this regime. And I'm not sure that I have a strong personal view as to what exactly characterizes the theory of general relativity. Perhaps that's something for further discussion. I'm not sure I would want to characterize what I think the core of the theory is right now. But in terms of thinking about how the models, so what people in the field are thinking about in terms of the sense in which the models depend on GR. So I think one of the worries here is this issue of degeneracies. So when it comes to talking about people talking about numerical relativity, it's often presented in such a way that these are just solutions to general relativity. And I have not seen much discussion of the sense in which it depends on, it is almost presented as just like solutions. And that's obviously not being careful, but it's very much presented as like very strong ties to the particular theory. In terms of the other modeling approaches, I'm not sure I've really seen much discussion about exactly about the issues that you're trying to to talk about. But what your question did sort of remind me of is like, what would it actually take to sort of see that these models were inaccurate? And I think one of the things that I'm most concerned about here is the issue of degeneracies, where you could have theories that were basically giving you the same models, but the systems that produced the signal, that same signal would actually be different. And that's the kind of sense in which I'm thinking that the models depend on GR. It's the sort of backward sense in which, given this signal, what kind of system is actually associated with that signal. And if it is the case that the sort of parameters that we're inferring about the system are different from the ones that you would say based on your analysis from general relativity in these models, then that's kind of, at least for me, the most important sense in which GR could be wrong, and that these models are assuming in some way they're assuming GR. So I don't know if that answers your collection of questions.
That's very helpful, thank you.
I just had a follow-up on Eric's question. So, oh wait, but I see there are two hands. So let's get the hands done, and then if we have time, I'll have a finger on this hand. So Richard, why don't you go ahead?
To go back to my last point on comparing the importance of systematic versus statistical errors here, usually when we get a result like the Higgs boson being detected or LIGO's detection, we're going to get some very exquisite, like 5 sigma statistical errors, and then that leads us to believe that the systematic errors, or it should lead us to believe that the systematic errors may be the most relevant errors in what your result is. And I think that but statistical errors are very well controlled in that we usually have some sort of mathematical distribution that we know the properties of, like, oh, well, these errors are distributed like a Gaussian, and previous experiments have shown that, and we know exactly how to quantify these errors. But for the systematic side, quantifying these errors becomes a little bit less straightforward, because they could be coming from any source, whether it's a wire that you haven't accounted for, or whether it's a template that's not realistic, or whether if the set of templates are not a representative set of templates. So I was trying to ask before, how far are we along in controlling the systematic types of errors, and how confident are we that even the statistical errors won't change a lot based on what we've done for our assumptions that would feed into the system, into the systematic. So I was, right now, do we think that we have the systematic errors fairly well controlled, nearly as controlled as the statistical part, or could there be more than just noise that's giving us false results, and should we be quite worried about that?
So I guess I'm reluctant to try and give some kind of estimate as to exactly how under control systematics are, because it's the kind of thing that it's the things that you don't know that are going to bite you. But I mean, I think one strategy that's often employed here is taking a sort of, I guess, robustness style approach of like having different avenues into evaluating whether something's going wrong. So the fact that you've got the modeled search and the unmodeled search, and that each of these is giving you I mean, not identical results, but you know, you're detecting the same things and they look pretty much the same. I think in terms of the gravitational wave detection, I mean, of course, there are a whole host of systematic problems associated with a massive, complicated detector. But they're doing all of the normal kinds of things that you do in order to try and keep those under control. I mean, once it comes to systematics associated with observing the binary black hole mergers, I mean, I think it's just a really hard problem to evaluate exactly how well under control they are for some of the reasons that I talked about. Of course, to some extent, the fact that they have had one observation with an electromagnetic counterpart does seem to indicate that things are pretty much going okay. I mean, they thought it was going to be a binary neutron star merger, so they thought it was going to have an electromagnetic counterpart. Lo and behold, they did observe the electromagnetic counterpart, and it's sort of all of it, you know, the many observations of that counterpart matched very well with the sort of models of what you would expect that kind of how you would expect that kind of system to evolve. So at least on like a very coarse-grained level, it seems that things are working well. Once you get into sort of the nitty-gritty of determining exactly the nature of the source system, things like the masses, individual masses and spins, which are very difficult. Yeah, I'm not sure if I can really comment on exactly how under control things are there.
All right, well, it seems like everyone's being cautious, and that's good. Thanks.
Yeah.
All right, Carl, please go ahead.
Very good talk. I enjoyed it. I wanted to ask about the circularity thing and as a source of theoretical bias problems, sort of the same question that Eric was asking about. It's a lot harder, I think, to find realistic examples where a genuine circularity fools you because, as it were, you're making some assumption that is used in the interpretation of the data in just the right way so that you misinterpret what you're seeing in a way that reinforces the initial hypothesis you were making. I mean, I think there are a few examples that we find in the history of science where that happens very temporarily with very early stage stuff, but I don't think it's very easy to find. But still, if you were worried about it, it seems to me like what you might want to do is just try to do all the analysis of the detectors and what you should be looking for in the templates and so on with several different kinds of theories other than GR that do differ in important ways from GR, but nevertheless are somehow physically respectable or reasonable, maybe Brand-Sticky or just plain old Newtonian mechanics somehow, if you can make that work. And so I was wondering if that's even something that anybody has discussed, like just trying to do a little bit of analysis to see, okay, what would we be looking for and what would be, and what happens if we pretend like we all believe, I don't know, Brand-Sticky instead of GR, then what would we do with this LIGO data?
Right, so I guess a couple of things to say here. First is that what I call the parameterized deviations test, this is kind of an attempt to do that. Now, it's not basing it on some other particular theory. It's actually, it's just doing sort of generic deformations of the waveform and introduced by these sort of, not exactly, you know, physical parameters, and redoing the analysis using this sort of more generalized set of templates. And so this is precisely trying to get at the fundamental theoretical bias problem. Because of course, if you use this more generalized set of templates and you end up getting, we'll say your analysis indicated that the one, you know, say if you have these extra parameters and they're supposed to be essentially deviations from GR, and there's sort of one in the middle where all of those values are 0, and that's the GR template. if your posterior distributions make it very unlikely that GR is the correct, that template is like the right one and those parameters are right on this analysis, that would give you good reason to be concerned about the fact that you were assuming GR. Yeah, as a matter of fact, the tests they've done are, you know, consistent with general relativity. So, so that's one attempt to sort of do what you're suggesting. The only other thing to say, I guess, is that one of the problems you run into in doing doing the same kind of analysis that the LIGO-Virgo collaboration is doing using alternative theories is that you just don't have well worked out results. You can't generate the difficulty of generating 250,000 templates for GR, which at least, I mean, it's not like we have like an amazing handle on solutions to GR, but we do have a much better handle than we do for most of the alternatives. You know, trying to replicate that for other theories, that's something that would be nice to do, and it would certainly cut against the circularity concerns, but it's going to be really hard.
Thanks.
All right. Do we have any other questions?
Yes.
Yeah.
If there is some time, I put this on the chat last week already. So I guess the EHT, the Event Horizon Telescope picture of the black hole in M87 faces very similar problems. I mean, the image is based on models, and there are similar circularity problems, I believe, and your entire analysis, well, seems applicable to that case. Have you thought about that? Or what would the differences be? What would be the similarities between these two cases?
Right. So this is something that I've maybe just started thinking about, really. I do think you're right that there are some sort of similar circularity problems, and that you know, you're basically sampling the visibilities with the EHT, and you've got very sparse, noisy data, and just sort of in principle, you have to make some kinds of assumptions in order to go from your measurements to some kind of source image, and it's always going to be a bit of a balancing act between making enough assumptions that you're doing something informative, but making not so strong assumptions that you're sort of building your conclusion into the process. I mean, I don't think I have anything very detailed to say at this point about you know, evaluating the various methods that the EHT has for trying to, you know, these different pipelines of analysis that they have, the different kinds of modeling approaches that are being used. I think one other feature that the EHT case in which it's sort of different is that, I mean, there are a lot of other observations of galactic centers to sort of constrain things like the mass of the supermassive black hole. So that might sort of be a relevant thing for, you know, having that sort of independent access to the system might help you a lot in thinking that the models that, you know, that the modeling is not actually a source of concern.
Right. Yeah, so they might win the Nobel Prize tomorrow, so then they'd better be non-circular. All right. Thanks.
I see that Jacob has a hand.
Thanks. So just building off of Eric's earlier question and Carl's question, I'm really interested in this question about what alternative theories of gravity we could, in principle, be generating templates from and comparing to the results coming out of the detectors. I think maybe it was Eric who pointed out that, it was Eric, I apologize, Eric, if this wasn't you who pointed it out, but you know, we're talking about GR in the vacuum case, and there are a lot of different seemingly self-consistent alternative theories of gravity that agree with GR in the vacuum case. So on the one hand, it's not entirely clear that we can distinguish between all of these different theories. But that, of course, then raises the question. To follow up from Carl, who suggested a couple of possible theories. You mentioned the Bronsted theory, maybe some concoction using something quasi-Newtonian. Do we have any, this is not just a question for everybody, do we have any, you know, internally consistent, fairly robust alternative theories of gravity that would be relevant to the vacuum case, that it would make sense to generate templates from?
So if you're punting that to me, an obvious candidate would be unimodular gravity.
Okay.
Yeah, and also a lot of Lovelock-Lanczos theories of gravity are going to agree in vacuum. Those are just two that spring to mind immediately. Almost certainly, there are going to be some more exotic possibilities, like various theories that depend on topological parameters, like Chern-Simons terms, that will be trivial, or more or less trivial in black hole spacetimes. We'll still agree in the vacuum case with standard GR. So you really do have an enormous family of alternative possible space-time theories that will agree in vacuum.
Great. Yeah, that's exactly what I was looking for. Thanks, Eric.
You don't want to look for ones that agree. You want to look for ones that are somehow different, and it doesn't matter if they're ruled out by other observations. Really, from the way I was thinking about it, the point is to look for just as a probe of the circularity, whether the circularity built in your whole technique is something you really need to be worried about or not.
Yeah. Oh, go on, Eric. I'm sorry.
No, please, Jacob, go on.
I was just going to say that in tests of quantum mechanics, for example, right, there's been an industry for decades of coming up not with alternative theories of quantum theory, but with broader classes of correlations that are non-local, but in keeping with certain basic principles that we expect to hold. And this is just my ignorance here, but I don't know if there's the same, you know, in GR, we like to start from a particular theory and then, you know, generate phenomenology from it. In quantum theory, we have this ability to just sort of write down all kinds of correlations that don't depend on having an underlying theory. And this makes it possible to compare the predictions of quantum mechanics against a very large class of correlations in like EPR type experiments. So this is actually just another open question. Is there some means in GR or in looking for, is there something comparable in GR for generating, I guess the analog, right? Empirical, you know, predictions that don't depend on having a detailed underlying theory. I mean, I don't know if the answer is yes, but.
So the very quick answer, and this is all I want to say, because I still want to hear what Martin and Grace still have questions I'd like to hear. But very, very quickly, the answer is yes. You can do almost everything you need for LIGO using nothing more than, basically using almost nothing more than generalizations of the Ricciardo equation.
Oh,
Martin, you're muted.
I was muted. Hi, Grace, please, your hand's raised.
Hi, thanks so much for the talk. I have another comparison question, just following on from what Klaus asked about the EHT measurements. I'm wondering how you think the circularity concern here compares with the circularity concern for analog gravity experiments, because there you also have an inaccessible target system, and you have a concern that you can only learn about the target system based on your experiment on the source system, under the assumption that your beliefs about the models for both systems are more or less true. So I don't know if this is a question you've thought about before, but I'd be curious to hear your thoughts.
Right, so let's see, I guess I tend to think of analog experiments more, in a way, less in the context of experiments and more as a kind of, you know, simulation. And so what you're concerned about is, you know, first of all, whether the sort of basic implementation of some kind of model, you know, is actually an accurate representation of the target that you're interested in. Mm-hmm. And so I guess you can make the comparison between sort of numerical relativity simulations and analog gravity experiments, in the sense that you know, you can have very careful control over the analog system and be really, you know, establish, you know, the internal validity of the experiment to some very high degree, depending on the, you know, control over the experiment you have. You know, it's always the external validity that's the problem. It's
exactly,
you know, whether or not you've actually, whether or not the system that you are dealing with, whether it's some kind of computer model running a simulation, or whether it's you know, a tank of water, and whatever you're doing with it. The real challenge is, you know, establishing that it's a good representation of your target system. And, you know, maybe the reasons that you would be cautious about that claim are going to be different in the two cases. But I think that it's in a way, it's a very similar problem. And yeah, it's a difficult problem to overcome, I think.
Do you think it would be accurate to say that there's more layers of modeling within the gravitational waves case? So in that sense, you don't have to worry about the circularity problem so much?
I would hope that the LIGO-Virgo case is better off, because at least you do have some kind of empirical grasp on the target system. Right. You know, you do at least have a signal coming from the target system of interest. So there's a sense in which at least the world has some way of pushing back. Now, the question is, you know, if it is pushing back, whether the methodology is well suited for establishing that it has. And yeah, so I guess that's kind of what I've been talking about in this talk.
No, that's
in the
really
analog experiment case, you know, if it turns out that the microphysics concerning hydrodynamics is, you know, is different from the microphysics of the vicinity of an event horizon, in the kind of way that their sort of behavior when it comes to something like Hawking radiation is different. No way that the analog simulation is going to be able to tell you that. And there's no way that the world is going to be able to sort of enforce it. It's very push back on the analog experiment. Whereas I would hope that with LIGO, that is the case. If, you know, maybe individual events make it somewhat challenging, but you would at least hope that with enough events and enough different observations of different systems, that we can start to become confident that that's not what's happening.
Right. Thank you.
So before I ask something, is there anybody who'd like to fit in a little question? We're kind of running out of time, but I think we have maybe just time for one comment or question. No. Okay. So I perhaps should have raised this point a while ago when Eric was asking his question, but so reach equals 0. Great. So it's obviously consistent with all kinds of right-hand sides. Okay. So one thing that I think could get beyond that is the memory effect, right? Looking at the electromagnetic memory effect. In that case, you pick up kind of correlations that depend sensitively on the way the stress energy tensor of Maxwell is linked, right? Is coupled to gravity. So do you think that I mean, so Jamie, yeah, what are your thoughts on the electromagnetic memory effect and whether or not that could kind of offer something a little beyond what's been seen and said so far?
Honestly, I'm not familiar enough with it to know exactly how that would play out. So maybe this is something that we can talk about another time. But yeah. Yeah,
I'm there's you know Lydia Bieri, have you seen her speak at the BHI?
No, I haven't. I mean, I just got here and I haven't been to many of
No, I know. I'm just wondering, maybe you had. Well, anyway, I'm gonna just link a paper of hers. So she's a mathematician, right? She does PDEs, but she also actually does physics. And so I'm just gonna link in the conversation a PDF of a paper of hers. It's actually a little old. It's from 2012. It's with Po-Ning Chen and Xingteng Yao, and they describe a little bit more about the electromagnetic memory effect. So maybe that's something to read at some point, either together or some other time.
Right. And the idea is that this might be some other kind of source of distinguishing between different.
So yeah, so the memory effect is regards the permanent displacement of test particles, if you will, due to right. Some signal that's passing through. Now Eric's point is I think a very good one, because Ricci equals 0 is the vacuum equation of GR, but it's the vacuum equation of any PDE, right, whose right hand side will have a little GAB that's coupled to any scalar quantity, so that when I say hit it with a pair of null vectors, I can kill those terms. So in other words, reach equals 0 is just kind of the vacuum sector, but the electromagnetic memory effect will pick up on exactly how TAB and little GAB are linked and are coupled. So I think it could offer maybe something new, something a little different from the things that we've been talking about.
So, I mean, one question I have from this is, how strong of an effect this is. I mean, is it the kind of thing that's likely to be detectable from?
This is where I invite you to read the paper, but it's rather small. The short answer is it's a very small effect.
At the risk of going overtime, I can say I hope one very brief thing, which is that no model that we use today that is remotely anything like that's used in LIGO, it incorporates electromagnetic effects. So we would really have to change. We would really have to dramatically expand our modeling capacity in order to take account of that. I think it's a really clever, nifty idea. It's just, but it would require, just from the viewpoint of computational tractability, I don't think we're anywhere near having the know-how to add electromagnetic effects and to the kinds of models we use right now.
Yeah, and I mean, plenty of gravitational effects are still being sort of neglected. I mean, things like the eccentricity of the binary are just being ignored, and it's,
in this vein, I think it's also important to remember that in multi-messenger astronomy, the electromagnetic models that are constructed completely ignore all the gravitational wave effects. They're just utterly independent. So you wouldn't even be able to use your idea in the context of MMA. But I think in principle, I think it's a really nifty idea.
Okay, but we're very far from it. Okay. I see. All right. Well, would anybody like to ask? I mean, we are really over time here, but Jamie, that's all credit to you.
I have one quick question, maybe a very quick question. How do you think that practical improvements in computational capacity over the next 10, 20 years are going to reshape all of this? I mean, I'd have to check the literature. I don't know how far we are off from Moore's law, right? But, you know, if you have enough doublings of computational capacity, does that radically alter this story?
So certainly, I think you could overcome the modeling bias aspect of it if you were using entirely numerical relativity simulations. I mean, still there's some legitimate modeling bias concerns. I mean, it's not like numerical relativity simulations are really outputting exact, perfect exact solutions to the Einstein field equations. But I mean, they're thought to be pretty accurate. So yeah, if you improve computation enough, I suppose that you could overcome that. I'm not sure it would make sense to, using numerical relativity simulations to, continue to explore the parameter space, and really make sure that your models are doing okay. I mean, they're already accurate enough, I think, given the sensitivity of the detector, but as the sensitivity of the detector increases, you need to worry more about having really, but I'm not sure that that's actually the most major concern right now anyway.
All right, well, let's give Jamie another round of applause for a lovely talk. And I think what I believe is the longest discussion that we've had. So either people happen to be very free today, or Jamie, what you brought to us was truly thought-provoking. So thank you.
Thank you all for your questions.
Bye-bye, everyone. Have a good rest of your Monday.
Bye. So I'm just Martin.
Yeah. So I've actually recorded it, so you don't have to do anything with the recording. You could just delete it, and that's fine.
A few people have written things in the chat. I just want to see whether what I need to follow up with, because people did that last week.